Welcome to Quantum Curious, and in today's lecture, I'm going to talk about a very interesting and peculiar type of quantum states of light. We have so far discussed some classical or rather quasi-classical state of light like coherent states, and we have also discussed some non-classical lights like fog state, and also we talked about thermal states and what kind of probability distribution they follow. But in today's class, I'm going to talk about another type of non-classical light that are usually uh, required or used in uh, some kind of task related to quantum metrology or quantum communication. So these states are called squeezed states, and they are very peculiar states and have very important uh, usage in uh, quantum technology related tasks. So let's see what are these states in particular. So we know that coherent states are described by, or all the electromagnetic fields are described by quadratures, and each mode can be fully described by pairs of quadratures. And these quadratures follow the Heisenberg uncertainty relations as they form the commutation relation that says that we cannot measure them simultaneously with absolute precision. So electromagnetic field have amplitudes that are uh, that have equal fluctuations, and they follow the uncertainty relation as they minimize the uncertainty. So for both the states, vacuum states and coherent states, we have quadratures that follow uh, Heisenberg uncertainty relation, but they minimize this kind of uncertainty relation as we cannot go further uh, deep beneath or deep down below this standard limit. So these usually cause 0 point fluctuations, and we usually encounter these kind of fluctuations and found them quite annoying if we are doing some kind of precision measurement on a quantum level. So there are another kind of special states called states, and they have some kind of less fluctuation in one quadrature at the expense of increased fluctuations in the other quadrature component. So we can make use of these kind of properties of squeeze states in in many quantum related or quantum technology related tasks. So these are very special case states, and they are usually hard to produce in laboratories. So we will see that how we can reproduce them or generate them in laboratories using some optical components and some quantum optical phenomena. So let's begin our treatment with a single mode of electromagnetic field, as it can be described by a single mode electric field operator. And we know that it could be written as this with annihilation and accretion operator. So we know that uh, annihilation and accretion operators are not that much useful in physical scenarios as they are not physical observables. So we usually write or like to write the electric field operator in terms of field quadratures that are physical observable as they are Hermitian operators. And they are found to follow the usual commutation relation as with the case of position and momentum of a particle. So we cannot measure them simultaneously with accuracy. So we have fluctuations of these quadratures in an electromagnetic field. And If we know these quadratures, we can fully describe our single mode electromagnetic field. So our task is to write the electric field operator in terms of these quadratures. So we can rearrange our electric field operator by using the Euler's formula and replacing the exponential with the trigonometric terms, and we end up with this expression. So here is k is missing, so it is a typo. So this follow this follows the Heisenberg uncertainty relation, and we could see that the multiplication or the product of the variances of both quadrature uh, should be greater or equal to 1 by 4. So this is the minimum uncertainty relation, as we cannot go uh, below this standard limit. So quantum states like coherent states and vacuum states are found to follow these kind of uncertainty relation. So this is different for different kind of states of light, like for Fock state and thermal states, these quadratures could be, or these fluctuations could be greater than this limit, but we can certainly cannot go below this limit. So this is the tricky point and an annoying uh, commutation relation or annoying quantum limit that is posed by nature. And usually we found that this uh, quite annoying for some experimental settings. So for vacuum states, these two fluctuations are equal and they are equal to 1 by 4. But for squeeze states, we can reduce the fluctuation in one quadrature at the expense of increasing the quadrature or increasing the fluctuation on the other quadrature. So we can decrease the quadrature, like we can decrease the quadrature of or decrease the fluctuation of the amplitude in the at the expense of increasing the fluctuation of the phase. But we can also reduce the fluctuation in phase by increasing the fluctuation in uh, amplitude. So we have to pay the cost, and the cost is to increase the fluctuation in the conjugate quadrature component. But we can make use of these kind of properties in many quantum related or quantum technology related tasks, as I have described earlier. So let's see how we can do this and how it is usually written in mathematical terms, and how can we extract some physical insights or physical phenomena that we can perform in order to achieve these kind of squeeze states. So graphically, they are represented by a phase-space diagram, as we have E1 and E2 as the two axes of our two-dimensional uh, space. And we could see that this complete circle is showing the vacuum state, as it has equal fluctuation in both the quadrature. But here we have reduction or reduced fluctuation in the E1 quadrature at the expense of increasing the fluctuation in E2 quadrature. So this is an ellipse in that case of squeeze state, and it is a perfect circle in case of vacuum or coherent states. So this is the basic difference in the phase space diagrams of these two states. So let's write the variance of even quadrature, say amplitude quadrature, and I want to reduce the fluctuation on this quadrature, and by reducing the fluctuation in this quadrature, the fluctuation in the conjugate quadrature E2 will increase automatically. So let's write it uh, in formal and mathematical terms. So we have the variance as it is represented by the, you can say, expectation value of E1 square and expectation value of E1 and its whole square. So using the expression of E1 in form of 1 over 2 and parentheses, A annihilation operator plus accretion operator, that is A plus A dagger. So using this form, we could write easily variance as this. And we want to use the normal order of operators by shifting all the creation operators on the left side and shifting all the annihilation operator on the right side. This could be done by using the commutation relation of A and A dagger. So using this, we could write or rearrange our equation as this. And then we have a normal order variance with a fluctuation or constant term that is 1 by 4. So we have achieved uh, the desired form that we wanted to show, and we could achieve the squeezing in this quadrature by decreasing this term or by making it negative. So let's see how can be done this. So similarly, if you want to as if you want to get a state with E2 squeezing, we can work out this form to get the squeezing in E2 quadrature. So again, defining quadrature operator and taking the normally ordered variance as given by this formula. So we have to calculate both terms in order to get the full desired variance. So first term can be computed as this, and using the normally ordered uh, relation by using commutation relation, we can write E1 square in the form of the normally ordered operators. So dropping the constant, as uh, it will give us the overall constant in the form of 1 by 4. We can get the even square expectation value in the form of normally ordered operators. So now compute the expectation value of E1. So we know that the variance is usually or always is a real quantity. So we want only the real quantity, so we will ignore the imaginary quantities for now. So taking only the real quantity, we get this. And taking square, we get this. So putting these values of normally ordered operator square and the expectation value square in the above formula that we have defined for normally ordered variance, we can get this. So grouping terms of using fluctuation operator as this, we can end up with these equation. So we can use our uh, in our formalism that we define to that we create or that we introduce to define the annihilation and accretion operator, as the expectation value is going to be or always going to be the complex number, as they have the magnitude part, that is the alpha mod, and we are going to have a phase uh, value that is going to define the position of the given state in phase space. So using this property, we could write the A dagger or A's annihilation A square expectation value as this, and expectation value of annihilation operator square as this. So only taking real part, we can rearrange the above equation as this. So putting all these values in the above equation, we can get the desired form. So we could see that by rearranging or optimizing the value of cos phi and cos 2 theta, we can make this overall uh, quantity as negative. And they are two interesting terms, as these terms are related to some physical phenomena. So this term is uh, is related to phenomena in which a light pulse or coherent pulse will interact with a nonlinear media and will generate two lower energy photons that would be entangled and squeezed. And on the other hand, this term is showing that we need to have a coherent state. So usually in order to uh, produce or generate squeeze state in laboratory, we need to combine both the phenomena, like a parametric down conversion and using a strong coherent source. But we could also do this individually, but it would be very difficult to do so. So usually the combination of both is usually used in laboratories to produce the or generate the squeeze state. So this is all for today. So we have discussed what are squeeze states and how they are different from coherent states. And we saw that how we can achieve the squeezing in one quadrature by using some simple physical phenomena in our laboratories. So thank you. If you like this video, kindly subscribe this channel, and kindly, if you have any kind of question or a suggestion in order to improve the overall content, kindly do comment below.